And we're back. I wanted to do a follow-up of yesterday's stream. Hello, Smart Coder. Hello, Lucia. Welcome. I was saying that I wanted to do a follow-up of yesterday's stream about the LeetCode's weekly 360 for to explain a simpler solution to Q4. I share the link to the problem again, and I'm gonna be sharing the video of the first part of this stream where I went over the entire contest. But now we're gonna focus only on Q4. And yesterday I was told during the stream by chat that there was a sure, yes, questions are welcome, a ton of them, the more the better. So feel free to ask questions, interrupt me. That's all good, all fair. So I was told that there was a binary lifting solution for this problem, and I did not think about it on my own. So when I realized, I thought about it, and I managed to solve it using that technique. So I wanted to explain my thought process and my code, because I think it's a lot simpler. My code, my first solution was a little long and more complicated, I think. So I already did a video explaining binary lifting. So I'm not gonna dive deep into the technique itself. I'm gonna share also the link to that video. So I'll recommend you to watch it, and if you're watching this on YouTube, you can pause this video and maybe watch the other one first, as you wish. I'm still going to explain a little bit what I'm doing, so don't worry if you don't know the prerequisite material. Anyways, so let's go back to the problem. I'm not going to read the problem statement again. I shared the link, so you can read it if you haven't, but I do. So this is my previous solution. Like I said, it's pretty long, like 70 lines. So I'm not going to read the problem statement fully, but I want to explain the problem. I want to explain the problem, but the abstract problem. I don't think the story about baseball is useful to understand the problem, so I'm gonna skip that part and explain the problem, but in more abstract terms. So we are given a function called R. Let's call it R, which goes from domain 0 to some n-1, so and to the same codomain. So what we figured out yesterday is that you can understand this function as a graph, as what it's called a functional graph, where every node. So, for example, you're gonna have for value 1, you're gonna have maybe value 3, and for value u, you have some b within this sets. So you can interpret this as being an edge, a directed edge from u to b. So the input, it's essentially a directed graph where every node, every of the n nodes has only one outgoing edge. So that's essentially the input. Then what are we asked to do with it? Well, we are told that we need to follow a path starting from choosing a node between all the n nodes as the starting node, and then following a path from that node of length k, which is another input, and it's pretty big. It's within 1 and 10 to the 10. And so you start from some u, for example, any node, and you go over k edges, and you add up the values of all the nodes in the path, and that's going to give you. So yeah, the nodes are labeled. So u, b, w, and maybe w goes to itself. It has a loop because, of course, there's no restriction. You can have r of w equals w. So here, if you are going to make, I don't know, so let's say you start at u, you make 1 step, 2 steps, 3 steps, then 4 steps. So that will mean that you have u first, then b, then w, and then w. So that would be 3 steps, for example. So that means that the score of the path starting from u for k, given some k equal to 3, is this sum. So notice that w is counted twice because you have a loop, and if k was bigger, you would have more occurrences, more terms of w. And you're asked to find the maximum score. So for every, starting from every node, you can have different scores. You need to find the maximum. So that is the problem, essentially. Okay, so yesterday I did some. You can watch the video, but I used a very complicated solution that was based on the structure of the graph. I'm breaking it down into cycles and non-cycles and traversing it more than once. Okay, so, but I did not think of using binary lifting. And I think the reason is that when I learned the technique binary lifting, I always associated it with trees or even forests, but essentially trees. And it turns out that that's not quite right. The technique works for that. That's why I didn't come up when I was thinking about the problem. I never thought about like binary lifting, but my mistake was that binary lifting is a more general technique, and I think the essence of when you can apply it is it's not a tree or a forest. It's a functional graph, which is what we have here. So functional graphs, like we see here, can have loops. That means that they are not trees. but they have some similarity to trees. That's why they are sometimes called pseudo forests, because what we discussed, as we discussed yesterday, they have the number of cycles by connected component is limited to 1, I think. So that's why they are pseudoforests. They do have cycles, but only 1. Anyways, so yeah, so why is this the condition for using binary lifting? Well, what it matters is that it's this condition that when you are at a node, you need to have only one next node, one successor, or one parent, if you will. So it doesn't matter. So and that's satisfied for that's exactly the property that we discuss here. That for every node you have exactly one successor or one value associated, one other node associated with it, and that is the necessary condition for using binary lifting. Because in binary lifting, if you remember, we're jumping from one node to its ancestor, if you interpret this as parents, and you can also call them successors in a more general sense. And so we're making jumps, and remember that when we're making jumps in a tree, moving from nodes to their path to the root. And remember that one technique was to add a loop, self loop, in the root, so that we could make potentially very big jumps and stop at the root without having special conditions. So even when we are using this technique, the technique of adding this loop, which is kind of a sentinel or kind of an imaginary loop, but this demonstrates that you can have loops in binary lifting, and that's why we can use it in this more general kind of graph. This loop doesn't have to be of size 1, it can be of any size. So so what we said is that the shape of this kind of graph is what we said yesterday, is essentially, you can think of as connected components as having one cycle, which we represent this. The curly lines means that these are paths that could have 0 or mode nodes in between. So here we have a cycle, and we can think about that as the center of the connected component. We are discriminating 3 nodes, but this could be even only one node with a loop, it doesn't matter. And then these nodes here are the root of trees. So, and this one can have another node here and so on. So this is the shape of the, I say the word shape because, or we can think about the structure. So it is an abstract way of simplifying how the graph looks like, because this is useful to understand why we can use this technique and why this is similar to a tree. So, and this, there could be more than one connected component with this shape, but in any case, the necessary condition boils down to what we said earlier, that for every node we have only one successor. So that means that we can compute the next successor, and it doesn't matter if there are loops. We're gonna do the jumps as we did. So without further ado, let's start with the code. So let's reset and let's start over. So we want to, so what do we need to do binary lifting? Well, we need to first find the parents or the ancestor, the one ancestor or the parents of the nodes, okay? And we do that with DFS. We're gonna do that with DFS. So we want to start filling the table of ancestors, and the size of the table is going to be, on the one hand, it will depend on the number of nodes. Let's call it n. And then it's going to depend on this, what we call a log, which is the maximum power of 2 of the jumps that we are going to make. The jump that we want to make at most is k, right? Because that's what we are asked to do. We want to make a jump from the initial node k times. But we're going to break k down into powers of 2. So we need to know what's the maximum power of 2 that k, when we decompose k, the maximum power of 2 that we could have. So k is at least 1. So at least 2 to the 0. So this is going to be the size of the table, right? So that means that we're going to have the powers of 2 from 2 to the 0, 2 to the 1, so on, up to 2 to the log minus 1. So if log is 1, it means that we'll have up to 2 to the 0, which is 1. But if 2 to the log is still less than or equal to k, then we need to increase log. Okay, and that's gonna give us, we could hard code this to calculate this for the maximum k, but this is a little faster. If I think in LeetCode it matters what the average order of complexity is, so I think it matters to optimize for cases. Anyways, so yeah, those are the size, those define the size of the tables that we need to fill to do binary lifting. So one such table is going to be the ancestor table. So this is a table with log rows for all the powers of 2, and then the columns are the number of vertices. And like we said, this is going to give us, so ancestor of I and U is the 2 to the ith and ancestor of u, right? And then we also need to know how much we have to sum for this jump, right? Because we don't only want to reach the end of the jumps of the jump of k, we also need to know what the sum is. So we're going to have another table, call it how do we call this, like the sum, the path sum. And let's initialize it with 0, and the size is going to be exactly the same. This is a parallel, because for every jump that we do, we need to have the path sum, the corresponding path sum. Okay, so this is it. Now we're gonna run DFS to initialize. So we need to initialize ancestor of 0 and u for every u. So we're gonna call DFS. DFS is going to do that, to initialize this. And so we do the standard DFS. So we have a visited array. Yes, we need this because we have cycles. So initially it's false. Then we go over all the nodes, and if it's not visited, we visited. And then we have the recursive function, and we mark u as visited. We go over, well, we only have one successor, that's the point. So this is going, let's call it be the receiver of u. And that means that the ancestors, now we do the initialization. So this is going to go, this is going to visit all the nodes in the graph, okay? And so we need to initialize this for every u, as we said. And the successor of u is b, okay? The one successor, or 2 to the 0 successor is b, or the parent. There are many names for it, but this is what's going to be our seed to then compute the whole table of jumps. So in this particular case, we're saving the successors in the path instead of the ancestors. No, I mean, successor is another name for ancestor. That's what I'm saying. So parent is equal to successor, or to the 0th ancestor, the first ancestor, sorry, or the 2 to the 0 ancestor. Those are all the names. So let me clarify this because it's getting confused. But so this is the successor. I'm using successor for the same equivalent to parent, which is equivalent to first ancestor, which is equivalent to the 2 to the 0th ancestor, which is equivalent to the ancestor 0 of u. Yeah, so this is successor of u, parent of u, first ancestor of u. Okay, now I think it's clear, right? These are all different ways of saying the same thing, but sorry if it was if I'm complicated things, but anyway, so then we continue. If it's not visited, then we visit it, and this is the standard DFS, nothing fancy here. Standard DFS with only one adjacent node, and this is it. So now that we have initialized the table for the first row, we need to we need to fill the other rows and the path sums. Okay, so let's first do the path sum for, I think we need to do this for 0 first, right? Yes. So for every node, we want the path sum of u to be the ancestor of u, the 0 ancestor of u. Okay, because we are considering only one edge, only one directed edge, and so let me clarify this a little bit because it's a little tricky. So here, when we said that we started from u, well, I think I deleted the graph, but here when we are considering node u, then node b, then node w, and this loop, and we start the score from u. What I'm doing is that, so b is the successor of u. So I'm saying that the path sum of only one edge that starts from u is equal to b. So this is my convention. So that means that if I start from u, I'm gonna count only b and w and then w. So I need to remember when I want the total sum to add u to the sum. Okay, so that's a little detail. So the path sum that I'm going to compute is not going to include the initial vertex. I'm gonna add it separately, so bear with me. Okay, so we have updated all the path sums for only one edge. So now we go for the whole things, for all the ancestors, but starting from 1 because the 0th ancestor, the 2 to the 0th ancestor is already computed, and we need to consider all the nodes. And so this is the typical binary lifting, right? We want to jump. We want to make a jump of 2 to the I, starting from u, and that's going to be two jumps of 2 to the I minus 1, so half the jump. So, but we want to do one jump of half. So if I is 4, for example, well, if I is 2, that means it's 2 to the 2, which is 4. So if the jump is of size 4, we want to do 2 jumps of size 2. So one starting from B. That gives us the successor, the ancestor after a jump of 2. And then we want to jump from there, another jump of 2. And that gives us the ith ancestor of U. All right. Oh, so yeah, this is not you. This is not B, it's you. It's not me, it's you. Anyways, so, and we need to do the same for the path sum. And like we said, this is a parallel kind of a table. So we want the path sum of I minus 1 from the half the jump from u, but we also want the path sum of half the size, but from the ancestor of I minus 1 of u. Okay? So now we have the table ready, so we can start the actual algorithm of considering starting from every node. So let's call it u from all the possible nodes. We want to compute the, let's call it the current sum for starting from u. We said that we needed to include u initially. And so we are going to do something here, some magic here, and then we are going to have a candidate, and we update our maximum, and we're going to return that. So what's the magic? The magic is the same that we did in the binary lifting video. We want to go over all the powers of 2. We want to decompose k into powers of 2. That means that we see for every power of 2, we see if that bit is on for k. And if it's on, we make the jump of that power of 2, which is, so we want to compute the score for, well, it's not the score here, it's called the path sum of jump 2 to the I from u. And we add that to the to the sum. And then we want to make the jump update u. So that is the ancestor I of u. And that is our magic. It's not so magical after all. And this is all there is to it, believe it or not. It's a lot simpler. So we have a mistake here. Line 36. So, what are we doing here? Ancestor. It's not subscriptable, so it is interpreting. Oh, so maybe oh yes, this is wrong, I think. So here we had, yeah, this should be 0 and u. Yes. Okay, it passes the examples and accepted. All right, it was easy. Okay, so smart coder, fire. You said you had tons of questions. Pretty cool, yeah. G to the G, where are the questions? You threaten tons of questions. Surprising that we don't need any special handling for the cycles. Yeah, this is awesome. I think this is one of the greatest problems that I've solved lately. I've learned so much with it. I'm very happy about it. Fuck binary lifting. Well, I can explain a little more about binary lifting. I think it's not a big deal if you think about it. So you want to learn all the ancestors from a given node, and so when it meets this with this problem, I am lost. All right, so yes, what I explained was that we are generalizing the application of binary lifting to functional graphs, or they are also called successor graphs. But it's essentially the same type of, it's the same algorithm, the same ideas apply, but so the only innovation in this problem is that we are doing this another table with the sums. We are not only jumping. Draw a short example. Yes. Is this good enough? Okay. So let's draw the graph. So we have nodes from 0 up to 4 inclusive. So 0 goes to 1, 1 goes to 1, then 2 goes to 1 as well, 3 goes to 2, and 4 goes to 3. So notice that this has the structure that we said, right? We have this central cycle, and then we have a tree from the node in the cycle is the root of a tree. So this actually is pretty much the same as what we do usually in binary lifting. We have a tree, and we add this loop at the root. So we are computing 2 tables here. First is the ancestor table. The ancestor table, which is going to have a size. So here, what is log? The log is, so k is 3. So we only need powers of 2 to the 0 and 2 to the 1, and that's it, because 2 to the 2, 4, it's already bigger than k, so we don't need them. So 3 is 2 to the 0 plus 2 to the 1, so that's how we decompose. So 3 is equal to 1, 1 in binary, or in other words, it's 2 to the 0 plus 2 to the 1. So we only need to know how to jump from make jumps of size 1 and size 2. So that means that the table will have only 2 rows. And 5 columns. All right. So this is 0 and 1. This is 0, 1, 2. 0, 1, 2, 3, and 4. So this is n, and this is I, the exponent. So we first compute the successors, right? Which is row 0. So that means that 4 has successor 3. 3 has successor 2. 2 has successor 1. 1 has successor 1. And 0 has successor 1. Which is essentially this. I mean, well, it's exactly that already. And then we compute, with binary lifting, we compute now this in terms of jump. So we want a jump of 2 to the 1 in terms of jumps of 1, 2 jumps of size 1. So from 4, we wanna make a jump of size 2. So that means that we jump to 3, and then from 3 here to 2. So we can know how to make this bigger jump by looking at this part of a table. Okay, so okay, this is binary lifting. I don't know if you want me to be so detailed about this. So essentially so now from 3 we go to 2 and then to 1. So this is 1. From 2 we go to 1 and then to 1. So this is 1. And then from 1 we go to 1 and then to 1. And from 0 we go to 1 and then to 1. So yeah, this is expected, right? Because if we're jumping, eventually we'll all end up here in the loop, right? If you make bigger jumps. So if you make a jump of 3, then everything is going to be 1. All the ancestors are going to be 1. Okay, so now we also want the other table, the path sum, right? Which is the same size and same meaning of the okay. So again, we jump from 4 to 3, and we said that we are going to consider only the value of the node that we go to, that we land into. So from 4 we will add up 3. From 3 we add up 2. From 2 we add up 1. From 1 we add up 1. From 0 we add up 1. And then when we jump 2, so the successor, we add up 3, but then we add up from 3 to 2. So we get 5. Then from 3, if we jump size of 2, we're going to add 2, but then 1, so it's 3. 2 and 1, 3. So here 1 and 1, 2, 1 and 1, 2, and 1 and 1, 2. How did you get 5? Yes. So from 4, so we said that path sum of, in this case, 4. Wait, so we're jumping. We're making jumps of size 2 or 2 to the 1. This is from node 4. And we said that, well, let's continue here. We said that this is equal to path sum of 0. So a jump of 2 consists of 2 jumps of 1. So this means 2 to 0 is 1. And from 4, which is, so we want to fill this number, and it's going to add up this number. But then we're going to add the path sum of 0, but from the ancestor of 0 and 4. And what? So we look up this table, and the ancestor, the 0th ancestor, the 2 to the 4, the 0 ancestor of 4 is 3. So then we go here to this column, and we get a 2. So that's why. So let's say this is 3, and then this is 3, and this is 2. So that's why we get 5. Okay, and so on. So yes, once we have these tables, great, makes sense. So once we have these tables, it becomes pretty straightforward. We just decompose k into powers of 2, and we make those jumps, and that means that eventually we're gonna make a jump of size k, decomposing k into powers of 2. There's not much else to it. And we first sum the path sum of that jump, and then we update the node that we're standing on. So u at the end is going to be the node, the final node of the jump, but we don't need it here. And there's this catch that we only included the node that we moved into the node of the value of the successor. So we haven't counted the value of the initial node. So that's why we initialize the sum with u, and then we update the maximum. So yeah, so I think it's clear. I think this kind of comments were useful, don't you think? I feel that this is useful. I will start doing it more often. I sometimes try to avoid comments in code. Yep. I sometimes try to make code as readable as possible and self-documented, but sometimes it's useful to have some good comments, not just repeating what the code says always, but also in competitive programming, or sometimes you try to make code more concise and not so readable. So it's useful to complement the code with some comments. So yes, I will adopt this convention. All right, so yeah, that was 50 minutes. I thought it would be like 30, but I think I'm satisfied. Cool. Yep. I'm satisfied with what we covered. We went over the let's do a lead room. No, I'm gonna finish. I wanna finish the. Never saw this application of lifting before. The formula is so aesthetic. Yeah. That's some big praise coming from you, NCC. Thank you. Yeah, that's how I taught it in the video. So if you are curious, you can check out my other video. You looking for more hard problems? Yes, I'm not taking requests. I wanna prepare a little bit so that I do. I have two kinds of streams. One, most of them are like a little prepared, like this one. But then, let me share the submission before I. But yeah, I take requests in, but with some delay, if you will, so that I prepare them for harder problems, so that I can think of the best ways to teach it. But then I will do occasionally more freestyle streams where I improvised. I did one a few days ago. Oh yeah, you can plug in your Discord, Smart Coder. I use the Discord to promote some of the content and to give a notification before I go into the stream, maybe so that people can read the problem that I'm going to explain in advance and give it a try. Yeah, no worries. Yes, I was told that you had that kind of addiction measure. Yes, Smart Coder told me about it. Sorry. Well, he didn't say it that way. He used the same expression as you did, but I'm interpreting it as a kind of a anti-addiction measure. Anyways. Yep, he does. Yeah, thanks guys for the support. So today cool. That's the invitation to Smart Coders Discord. I recommend it. I think this we're building up a great community. I was going to mention that today I became an affiliate of Twitch. So you can subscribe to my channel if you want to, maybe with Prime Video. So that, yeah, I would appreciate that a lot. Oh yeah, I think you have to troubleshoot that with the Discord support. But yeah, I recommend to join it. So okay, I'm gonna finish the stream now so that the video is more focused on the problem, and then maybe I'll do another stream to do some freestyle streaming. Anyway, so thanks a lot guys for the support. You're some of my biggest supporters. I really appreciate it, and yeah, check out all the content that I'm making. Bye bye.